Okay, so let gamma 1 and gamma 2 be subgroups of GL2 plus Q. And let alpha be in GL2 plus Q. In an earlier lecture, we discussed double cosets. The double coset gamma 1 alpha gamma 2, this double coset consists of all elements consists of these elements. Now observe that gamma 1 acts on the left for this set, and gamma 2 acts on the right. And so we may be able to, we can decompose. So this is just a secondary comment. We can decompose the double coset as a union of ordinary cosets of gamma 1. So it's this fashion for suitable gamma j. In particular, so example, let P be a prime. And gamma be SL2Z. Let, before I used XP, I just want to make a fancy XP, the collection of matrices, set of integral matrices of determinant P. Determinant P, then XP, then XP is equal to gamma P 0, 0, 1 gamma. So I will leave this as example or exercise. In other words, all matrices of determinant P can be written in this fashion, are here. So I can describe the matrices of determinant P as a double coset. Integer matrices of determinant P as a double coset. That's a useful idea to have in mind. In fact, maybe I'll do this exercise. Maybe I'll just do it. So let's see why. Indeed, it's clear that this is contained. This gamma is SL2Z. This is a matrix of determinant P. Therefore, this is contained in XP. It is clear. Clearly, gamma P001 gamma is contained in script XP. I just changed my notation from capital X to script X because earlier I used capital X. I noticed that in chapter 8 I use capital X for anything, so I want to make sure this is different. All right, to show the reverse, let sigma be an element in here. By an earlier theorem of yesterday, we can write sigma as gamma 1 times AB0D. Remember the action of the Hecke operators. These were the double coset. These were the coset representatives for that action. So we can write this for gamma with gamma 1 in SL2Z. Okay, and AD of course equals P, and 0 is less than B, less than or equal to D minus 1. If A equals P, then D has to equal 1 because D times A has to be P. D equals 1, and B is 0. So we're done in that case. And so in this case, thus sigma. So what am I trying to prove? I'm trying to prove every element here can be written as an element in here. Okay, then sigma, thus sigma is in this double coset. Okay, if otherwise, if A equals 1, then D has to equal P. Then observe that 1B0P can be written as 100P 1B01. Right? I mean, so that's that. Yeah. And the matrix 100P can be written as 0 minus 1 1 0 P 0 0 1 0 1 minus 1 0. So the bottom line is so that I can write sigma then, which was equal to gamma 1. Now in this case A is 1 and D is P. Is then equal to all this stuff. It's whatever I wrote. So you take all these matrices, put them in here, 0, minus 1, 1, 0, P, 0, 0, 1, 0, 1, minus 1, 0, and 1B, 0, 1. 1. This one here. So 1B, 0P is being written in this fashion. And so the point is that this is a matrix in SL2Z, this is a matrix in SL2Z, and this is also a matrix in SL2Z. So this is an element of gamma P001 gamma. In other words, if I started with a matrix of determinant P, I can write it as an element in the double coset. Thus, okay. So this observation is going to help us to try to define Hecke operators for higher levels. And to do that in a clean sort of way, we'll define the following set. So this interpretation will be useful to define Hecke operators. So fix an n which is a natural number. Let S plus be an additive subgroup of Z. So for example, hence, S plus looks like M times Z for some M. Because the additive subgroups of the integers are all of this form. Let S cross be a multiplicative subgroup of Z mod n Z star, and we'll also use S cross to indicate the pre-image from Z to Z mod n Z. Okay. So we'll be a little sloppy there. Define the set Xn. So define this set Xn n S cross S plus. So it's three pieces of data, capital N S cross S plus. It's going to consist of matrices A, B, C, D with integer entries such that the determinant is n, and C and A are in S cross, B is in S plus, and N divides C. So this is the collection of integer matrices A, B, C, D such that the determinant is N. The first column, A and C, are sitting inside S cross, and B is sitting inside S plus, and N divides always C.
So the N is like a...
Yeah, these are the same. This and this are the same. Yes. Yeah. But S plus, I'm not particular about. That'll be just any old subgroup. But I'm going to insist that C has to be denoted by N. This N is the same as N. So under my old notation, this is a subset of that script Xn, collection of integer matrices of determinant N. Oh, sorry. Yes, C is not in. Just A is in S cross. A is in S cross, B is in S plus, and N divides C. Sorry about that. So what is this? What is this thing? Well, it's an interesting object. Here are some examples. Well, when n equals 1, if capital N equals 1, S plus is ordinary integers, and S cross is just simply the residue class, corresponding to Z mod and Z star. There's an empty set, I guess. S cross would be just 1. Then Xn will just be equal to that. And if I take little n equals 1, so this is one example, little n equals 1, then x1 n1z turns out to be gamma 1 of n. Remember what gamma 1 of n is. Collection of matrices, A, B, C, D, such that n divides C, and A equals D equals 1 mod n. This was your gamma 1 of n. So in special case, when I put little n equals 1, and I take these as my subsets, the multiplicative group of ordinary multiplicative group, just the identity element, just the 1. And here I take the full additive subgroup, I end up getting, you can just check, the conditions are there. AD minus BC is 1, of course. A is invertible, and so it has to be A times D has to be 1 modulo n, and I'm just trying to see why is D congruent to 1 mod n. Oh, because yeah, A is an S cross and A is already 1. Sorry, yeah, so that's right. Yeah, A and D are, yeah, that's right. Okay, that's fine. Okay, so that's one example. Let's see. Another example is gamma of n can be written as x1 of n. I'm going to leave these as exercises. And gamma 0 of n so you can just check those conditions and convince yourself that I can write all the various subgroups that I had already met in terms of this X notation. I'll also leave as an exercise that for fixed n, S plus and S cross, xm, xn is of course contained in xmn. So clearly this has determinant m, this has determinant n, therefore the product will have determinant mn. That's okay, but then you have to check all those silly conditions are satisfied. It's just matrix multiplication. I'll leave it to you to check that. All right. In general, x1 n S cross S S plus, this thing is a congruent subgroup of SL2. And if I pick n equals 1 here, you can see that x1 acts on xm on the right. If I pick m equals 1, you can see that x1 acts on the left on xm. Okay, so it's clear that, so we have a left action and a right action on this set. Notice, observe. That x1, xn is contained in xn, and xn, x1 is contained in xn. So we have a left action and right action. A left action and right action. Of x1 on xn. Now here's a little general exercise. Suppose that H is a group acting on a set X, on a set Y. I don't want to use X's because I've already overused them here. And suppose that the orbit space is finite. Suppose and that the orbit space well, it depends on how you write it. Some people write it like this, or some people write it on the y \h. But suppose this is finite. Suppose the orbit space is finite. In other words, the number of H equivalence classes is finite. Suppose that if H1 is a subgroup of H of finite index, and x is a subset of y, which is H1 invariant, under the action of H1. Invariant meaning it's H1 acts on X and it contains X. Okay, so then the orbit space is also finite. The orbit space X modulo H1 is also finite. So I'll leave this to you to mess around with. So you can write your Y as H orbits. Then you can see that X can be written as a bunch of H1 orbits. Then you write your H as a bunch of H1 cosets and then twiddle around and you get it, okay? So I just want to use this general comment. This has nothing to do with the general comment. This comment I will use now to make the following observation. So here, thus, we apply this fact as follows. We have xn being acted on by x1, so we can decompose xn as a bunch of these orbits. Now, the point is that this is a finite orbit space. This is a finite, so check that the number of orbits of x1 is finite. I want to say that. So how? I'd like to say this, but how do I say that? Well, the point is that first, that I apply this comment as because x1 is a congruent subgroup, it has finite index in SL2Z. So I'm going to apply this comment to the situation where this is my group H in that comment fact over there, and this is my subgroup H1. Okay, and we already made the comment that the matrices of determinant n with the special definition is contained in the script xn, correct? The script xn we met earlier in an earlier lecture. Those were matrices of determinant n with integer entries, right? So this is my y. Remember, SL2Z was acting on the matrices of determinant n, and we had a decomposition into a finite number of orbit spaces. Okay? So I applied in that fashion. So this is my H1, this is my H, this would be my Y, and this would be my X in this general fact, and then I conclude that the number of orbits of x1 under this action is finite without doing any work. With this decomposition in place, we'll now define the nth Hecke operator. So now consider, we look at the space. Remember, x1 is a congruent subgroup, right? And I look at the space of modular forms of weight k for that x1. And we define the nth Hecke operator, Tn of f, for f in mk of x1 to be n to the k over 2 minus 1 summation I f slash alpha I. So these orbit representatives alpha I will be used to define the Hecke operator. Okay. Now this tallies with our earlier definition of the Hecke operator actually. If you take the full modular group and do the same construction, it turns out that this is exact. These orbit representatives were those representatives that I had for matrices of determinant P. So it actually works. This generalizes the earlier, this agrees with our earlier definition of Tn for the special case of the full modular group. And so we have the theorem that if the Tn maps mk of x1 into mk of x1. And Tn maps sk of x1, space of cusp forms, into sk of x1. And you now know how to prove these theorems. You want to slash this with an element in x1. You use the fact that x1 xn is contained in xn x1. You use this decomposition, this particular decomposition. You twiddle this around and you end up getting. So these are basically now routine. And the cusp forms vanishing is again because you have, remember we did this calculation yesterday in the context of Peterson inner product. You needed to know the behavior of the function when you slash it with an element of GL2 plus Q. And we verified that cusp forms are still cusp forms under that holomorphy is preserved and vanishing is also preserved under that slash operator with alpha being an element of GL2 plus Q. Now, we will write down, so this gives us a general recipe of writing down Hecke operators for any arbitrary x1. So remember x1 can be gamma 1 of n is realized as x1, gamma naught of n is realized as x1, and all the subgroups that we've already met are realized as x1. Therefore, this gives us a general recipe for constructing Hecke operators for those groups. The analysis can be a little subtle, and so I'm going to confine my attention to the case gamma 1 of n. We will consider in detail Hecke operators for gamma 1 of n. So that's this group. We'll look at this particular group. So here's the theorem. For each A in Z mod and Z star, fix a sigma sub A in SL2Z such that sigma sub A is congruent to A inverse 0, 0, A modulo n. Here, A inverse is not 1 over A, okay? Here, A inverse is an element modulo n such that A inverse is such that A times A inverse is 1 mod n. So choose an element sigma A in SL2Z with this property. The fact that you can do this is an old exercise. Remember when you had an element mod n, you could lift it to an element in SL2Z? That was lecture 2 or something, okay? So we have that. Then xn, we already observed that xn is equal to xn n1 z. So this is your gamma 1 of n. And we have the decomposition sorry, this is not gamma 1 of n. So let's take that. When I put n equals 1 it is, okay? But take this, okay? Then you write xn. So let's call this xn. Xn can be rewritten as AD equals n, A positive, A and n relatively prime, B going from 0 to d minus 1, gamma 1 of n, sigma sub A, B 0 d. Okay, so this is our decomposition of the as a union of orbits. Remember, in the earlier case, we didn't have this element. Earlier case, we just had the identity element. So you had these matrices A, B, 0, 0, D, and we didn't have this coprimality condition because the level was 1. And so now with this particular decomposition, then I told you in the earlier recipe was to decompose xn as a union of these orbits and use these orbit representatives to define the Hecke operator. So f slash these orbit representatives. Okay. So everything is a disjoint union, so I hope this is all clear. These are disjoint unions. The first sum is over divisors of n, which are positive and co-prime to capital N. So let's prove this. Clearly, these terms here, sigma A is an element in SL2Z, therefore it has determinant 1. This guy's got determinant n. So all these elements are contained in Xn, and it's pretty clear. Okay, so this clearly the right-hand side is contained in Xn. Right-hand side is contained. You have to check a few conditions that I spelled out for these two things, but I'll leave that to you to do that. We have to show that the union is disjoint. So suppose not, and we have gamma 1 sigma A1, A1, B1, 0, D1 equal to gamma 2 sigma A2, A2, B2, 0, D2 with gamma 1 and gamma 2 in gamma 1 of n. Suppose the union is not disjoint, then the matrix A1, B1, 0, D1 times A2, B2, 0, D2 inverse that matrix is equal to, well, A1, B1, 0, D1. And you know how to calculate the inverse of a 2 by 2 matrix, so I'll just do it here. Divided by the determinant, which is A2, D2. So this calculation shows that it's equal to. So here you can see that it's going to be 1 over A2. So you get A1 over A2 star 0 D1 over D2. Which implies that A1, so this element is in SL2Z, and so therefore this implies that A1 equals A2 and D1 equals D2. Since the AIs are positive, and therefore I can go back and rewrite. I'm running out of space, so let me just continue here. So therefore we can write A1, B1, 0, D1 as 1 something 0, 1 times A2, B2, 0, D2. And so let's call this J. Since B1 and B2 are both less than or equal to D1 minus 1. See, we agreed that D1 equals D2, so B1 and B2 have to be less than D1 minus 1. But then this guy here is B2 plus JD2. Okay, if you like this, D2 minus 1. D1 and D2 are the same anyway, okay? So this is B2 plus JD2, and the only way that can happen is if J is 0. So that shows that these can't have that these are distinct. To complete the proof, we need to show that any element of Xn, that is, any element of here, is actually contained. So I've shown that the union is disjoint, but I still haven't finished the proof. I have to show that every element here can be written as an element here. Okay. And maybe what I'll do is well, I don't want to leave too much for Karam Dev to do, but let's just do it. I think it'll only take 5 minutes. So we need to show still that any element alpha, beta, gamma, delta in Xn lies in one of these orbits. Or orbits. So to do this, choose integers g and h so that g alpha, choose co-prime integers. Otherwise, any old integers, 0 would work. Choose co-prime integers. Choose co-prime integers g and alpha such that g and h such that g alpha plus h gamma is 0. I'll leave this as an elementary number theory exercise. And because alpha delta minus beta gamma is equal to n, and by our conditions alpha and capital N are relatively prime, so since this holds and this holds, there are integers, n also divides, by the way, gamma, divides the lower corner there. We can find integers x and y by the Euclidean algorithm such that x alpha, xh minus gy equals 1, because g and h are co-prime, so you can always do this. Sorry, this is part of this is just an aside. It's just an aside. After choosing g and h co-prime, we can find integers x and y such that xh minus gy equals 1, and set capital A to be the matrix xy gh, which now, of course, is an element in SL2Z. And now consider the matrix A times alpha, beta, gamma, delta, which is equal to x, y, g, h times alpha, beta, gamma, delta. And because we rigged it in such a way that g alpha plus h gamma is 0. So this is a matrix which is triangular. So this is 0. So I rigged it that way. And it has determinant n, which has determinant n. And I need to show that this particular matrix, this matrix can be written as has the desired form. What's the desired form? The desired form is some element of gamma 1 of n times that sigma A times that AB0D. So that's all we have to do. And for that purpose, that can be done we can always replace this by, so replacing A by plus or minus 1J01 A if necessary. We may suppose that our matrix now looks like A times alpha, beta, gamma, delta equals AB0D with A positive and B between 0 and D minus 1. So basically, I'm just applying the division algorithm. I could shift to make this B to be a representative modulo D, and I can multiply by plus or minus to ensure A is positive. That's all. And now It's just a question of seeing that that indeed is exactly the case that you want. And since S cross was just, S cross in our case was just the group, the trivial group, since S cross, since S cross is the trivial group, we have that A inverse has the form A inverse star 0 A modulo n. So the matrix A inverse modulo n has this particular shape, so which can be rewritten as 1 star 0 1 A inverse 0 0 A modulo n. That is, we can find a matrix, thus we can find a matrix B in gamma 1 of n, so that A inverse is equal to B times sigma sub A. So that means that if I started off with a element in the of determinant n in that of that particular shape, I can actually write it as so A inverse is written in this fashion, and remember we wrote our matrix alpha here. So here it is, A times alpha beta gamma delta is of this desired shape, and I'm trying to write my matrix alpha beta gamma delta as an element in the orbit space. So this alpha beta gamma delta is equal to A inverse times this matrix of this shape. But A inverse can now be written as B times sigma A. Therefore, my original matrix alpha beta gamma delta can be written as B times sigma A times this A B 0 D that I had. Okay. So that takes care of that proof. All right, now I think we're set to, with all these technical details out of the way, to define and study Hecke operators on gamma naught of n. And this relationship between things in gamma naught of n and gamma 1 of n, which I want to kind of specify. So here, we need to discuss what's called Neben Typists. So recall a Dursley character. So a Dursley character is a homomorphism from Z mod NZ star into the non-zero complex numbers. So therefore, it's a homomorphism, therefore chi of 1 is 1. And here's a little exercise. If gamma is an element in gamma naught of n, so remember what gamma naught of n is, collection of matrices A, B, C, D, A, B, C, D integers, determinant is n, determinant is 1, AD minus BC is 1, and then n divides C. These are the matrices that we have. Observe that gamma 1 of n is contained in gamma naught of n. Observe. Oh, I didn't finish the exercise, sorry. So gamma is this, and I want to define psi of gamma to be chi of d. You take a matrix A, B, C, D, and you define psi of gamma to be chi of d, and I claim psi is a homomorphism from gamma naught of n into C. So show that psi is a homomorphism from gamma naught of n into C cross. Okay, I'm hoping that you saw Dursley characters sometime in your life, but if not, let me give you a quick. So these are Dursley characters. They're very important objects in number theory. And the set of characters of Z mod n Z star forms a group under multiplication of characters, forms a under usual multiplication of characters. So if I have one character chi1, another character chi2, I can consider chi1, chi2, and that's again a homomorphism. And you have you have an inverse character, which is complex conjugate of the character, right? So these are all. Hopefully, this is familiar. Is there anyone who has not seen this stuff before? Okay, so that's good. You recall that there are these orthogonality relations that I'm going to use. Recall these characters satisfy orthogonality relations. Now this is actually nothing special about Z mod n Z star. This is always true for any finite group. Certainly finite abelian group, it's clear. If it's not an abelian group, the set of characters you can't make a group out of it. So that's the only problem. But since we're not dealing with non-abelian groups at the moment, we'll just stick to abelian groups. In the case of abelian groups, it's a general fact that characters of abelian groups, again, form a group. And you have these general orthogonality relations, but in this case, let me just write them down. If I go over all the characters chi of d, this is equal to phi of n if d is congruent to 1 mod n and 0 otherwise. And then you have the dual relation. The dual relation is if I fix the character and go over zero if chi is not equal to the trivial character, and phi of n phi of n if chi is the trivial character. So these are what are called the orthogonality relations. Hopefully, as I said, you've seen them in life some point in time. So we're going to use these characters to define a space mk of gamma naught of n chi is going to be the collection of modular forms of weight k on gamma 1 of n. So we know what that means. So this is something we're already familiar with. However, f slash gamma is going to be chi of d f for all gamma in gamma naught of n. So instead of transforming f slash gamma as f, we have this character. So remember what chi of d is. It's psi of gamma, the character that this character. This is what I mean by chi of d. Just take that lower left, the lower right corner element D and evaluate the Dursley character. So this is what we will call MK of gamma naught of n chi. And the relationship between this particular space, so we refer to, if we have an element of this space, the chi that corresponds to the form is called the Neben Typists. So for an element of this space, we call chi the Neben Typist. That's the word that's stuck in the literature. It comes from the German type of level, I suppose, or Neben. So here's the theorem. So this vector space here is a direct sum of these vector spaces. And this is as a decomposition into vector spaces, not as Hilbert spaces. I'm not talking about orthogonality with respect to inner products or anything like that at the moment. So we have this decomposition of this vector space as the direct sum of these vector spaces. Therefore, the study of these spaces is reduced to the study of these spaces. We have a similar decomposition. Sk of gamma of 1 of n is also a direct sum over chi mod n of sk gamma naught of n. Okay. Now, in the interest of time, I'm going to skip the proof of this theorem, except to point out that on page 100 of my book, there's a typo, and I want you to correct it. So typo on page 100 of text. It should be f chi instead of f on line 7. Line 7. So it's a small typo, but sufficiently serious in the sense that f doesn't make sense. So page 100 of the book, just want to make sure that I'm telling you the right thing. Yes. In other words, I said f is an mk of gamma naught n chi. No, it's f chi is in, okay? So, i.e. f chi is in mk. Okay, so the proof of this is not hard. So proof is not hard. Not hard, but makes essential use of the orthogonality relations. But makes essential use of the orthogonality relations. And I think if Karandev has time, you can probably just at least kind of go through some of the steps in that calculation. So now, recall in the previous discussion, in the earlier discussion, we defined Hecke operators for gamma 1 of n. Okay, so I realized gamma 1 of n as one of those x1s, and define the Hecke operators for that. So the question is, how do you define Hecke operators for these spaces? Because this doesn't fit into that formalism. These spaces don't fit. Right? The full direct sum does, but not these individual. So I may want to cut down the size of the space and study each individual component separately. And from that perspective, it makes sense to define for f in mk of gamma naught of n chi, we have f slash sigma sub a, that element, it's equal to chi of a times f. So we set Tn of f. In that case, actually turns out to be, so I can view my f in this space as an element here and look at what the Hecke operator is doing to it and see what's happening. So here I'm going to apply the map. So because I've rubbed off the definition, but anyway, f slash sigma a is that, so we can write it as chi of a summation b 0 to d minus 1 f slash ab 0d. Now notice that in the earlier definition I had ad equals n, a positive and a relatively prime to capital N. But now because chi of a as a Dursley character is only supported on coprime residue classes, therefore I can drop that condition. And the point is that this is for f in mk gamma naught of n chi, this turns out to be in mk gamma naught of n chi. So what you have to do is you have to show that when I take Tn of f and slash it with an element gamma, it's equal to chi of d times f, chi or psi of gamma, the way I defined it. So that's basically what you have to do. And so that's point number one. Point number two is a discussion about cusp forms. Also, Tn maps maps Sk and if you have a Fourier expansion of this shape, then Tn of f looks like m going from, actually you don't need to take a cusp form, you can take a modular form if you have Fourier expansion like this. The Fourier expansion here is going to be a divides m n chi of a to the k minus 1 lambda of mn over a squared times q to the m. So here is the direct verification, direct calculation of the Fourier expansion. And from this calculation, one sees that the behavior of the cusp form at infinity and the other cusps, you can deduce that the cusp forms actually go to the cusp forms again. So if f is an eigenfunction of all the Tn's, we say if f is an eigenfunction, we have lambda m n times lambda 1 equals lambda m times lambda of n for all mn relatively prime. So this shouldn't be a surprise, I mean, after what we've done all earlier. So in particular, choosing choosing what? Choosing m equals 1, let's just put m equals 1. Oh, so one more point is if f is an eigenfunction for all the tn's, say, I should say tn of f equals mu n f, then the point is that mu n, we have then mu n times lambda of m, which is the coefficient here, has to equal lambda of mn from this formula. And then comparing that, you see that lambda 1 cannot be 0. If it was 0, f is identically 0. So in the case f is not identically 0, lambda 1 is not 1, and so we can divide by, normalize it, and so that lambda 1 is equal to 1. So we normalize so that lambda 1 equals 1. And it turns out, so this is one of the calculations that you have. The other calculation is, of course, the recursion relation on prime powers. So whenever m and n are prime, you have this multiplicative property, so that's preserved. So that part of the generalization of Ramanujan's conjectures to the higher level is preserved. The second conjecture of Ramanujan was a recursion relation of these eigenvalues at prime powers. And that recursion relation, we also have lambda of p to the a plus 1 is equal to lambda of p to the a minus chi of p to the k minus 1, lambda of p to the a minus 1 for all a bigger than or equal to 1. So the second part of the conjecture is also clear. And of course, the third part is the famous Ramanujan conjecture. That if f is a normalized eigenform, it's a normalized cusp form, then lambda of p is bounded by 2 p to the k minus 1 over 2. And this is what was proved by Deligne. 1974 as a consequence of his proof of the Weil conjectures. So it's a tour de force of algebraic geometry, of course, beyond the scope of these lectures. And it still, unfortunately, in order to prove this, you have to go through that route. So there is no proof of this conjecture which does not make use of algebraic geometry, as far as I'm aware. There are proofs of weaker statements, which, yeah.
So in there you have said that let f be an eigenfunction.
A little louder, please.
Let f be an eigenfunction for all t.
Yeah.
First of all, do we know that such a f exists?
Well, yes, that's a good question, and the answer is yes, it does, but it's not a trivial fact. Here's what you need to do, and I was just going to make that comment right now, and that is you have to establish that the TNs are Hermitian with respect to the Peterson inner product, and therefore there exists a basis with respect to that Hermitian operator. So you have to establish a certain Hermitian property of TNs. Indeed, so let me just state that. And that's a little bit subtle because I've defined Tn's for all n's, but it turns out the Hermitian property only works for little n co-prime to capital N. So that's an important sticky detail. Sticky detail. So indeed, we can show that if n and capital N are relatively prime, Tn of f, the Peterson inner product Tn of f and g, turns out to be equal to f slash zigbus of n, comma Tn of g. So it's not quite as neat as possible. It's not quite good and clean. In particular, if f is in Sk of gamma naught of n chi, Tn of f and g is equal to chi of n f and Tn of g. So there's no, property that we had as before. So what we do this is the, in trying to show some sort of existence theorem as you request, you want to kind of establish that these Tn's are Hermitian operators, but they're not quite Hermitian operators because of this extra sticky point. So what you do is you consider, let Cn be a square root of chi of n bar, and consider Cn Tn. Then Cn Tn of f and g turns out to be equal to f Cn Tn of g. So this Cn Tn is a Hermitian operator. That has a basis of eigenforms. But I have to restrict myself to n and capital N relatively prime. So I can't do this for all TPs, but I can only do it for Tn's. And so this Hermitian property by linear algebra shows that there exists a basis of, by the way, I haven't discussed commutativity of operators, but again, the operators are commutative, so let's not worry about that. So you have a commuting family of operators, so you can simultaneously diagonalize. There exists a basis of eigenforms of Cn, Tn, but n and capital N relatively prime. This actually was very disconcerting. However, it was very unsatisfactory because you didn't have a basis of the Hecke operators for all Tn's, but only you had to confine yourself to Tn's which were relatively prime to capital N. And I believe Hecke was perplexed by this, and this was not solved by him. It was solved in the 1970s by Atkin and Lehner. So what I'm trying to say here is this fact that we have an eigenbasis only under this restriction is an unsatisfactory result, and the difficulty was spelled out in detail by Atkin and Lehner, and they saw the problem arises from the fact that you can have, basically the problem arises from the fact that we have to talk about where is the modular form really coming from, where is the level at which it lives. And this has led to the following, let me make the following definition. So our theorem gives a basis only for Tn's with n and capital N both prime. One would like a basis for all TPs, including P dividing N. Now the TPs preserve each eigenspace so for P dividing N, TPs preserve each eigenspace of all the Tn's with n relatively primed. So you look at these eigenspaces for the other Hecke operators, but the TP preserves them, that's fine. However, the fact of the matter is that these eigenspaces need not be, they won't be one-dimensional necessarily. So these eigenspaces are not necessarily one-dimensional. And so, in order to remedy this, we need a finer theory. And this is what's called the Atkin-Lehner theory. And let me explain what I'm trying to say. If you have an eigenform, if you have a cusp form on gamma naught of n chi, say, and R is a divisor of n, and F is an eigenform for all the Tn's with n relatively prime to capital N, then F slash R001 is also an eigenform. In other words, what is F slash R001? It's essentially F of RZ. So F of RZ is also an eigenform for any divisor R of n. And so this observation, along with a few more, motivated Atkin and Lehner to make the following definition. So we discuss a little bit what's called old forms and new forms. See, if D1, D2, let's say, is a factorization of capital N, then gamma of n is contained in gamma of D1, right, for any divisor. So any modular form of gamma of D1 can also be looked at as a modular form for, this is the basic problem. This is one point. So I can look at modular forms that live here also as modular forms here. So you have a map. I can just, it's the trivial map, the identity map, as it were, taking a modular form F in this space to the same thing in this space, via this map. The other point is if G of Z is equal to F of D2 times Z, then it's a small exercise perhaps worth doing if that G is actually a modular form gamma 1 of n. So if G of Z, I can look at this as a modular form on gamma 1 of n. So I can also do this construction. So there are these two little maps. One is the map that takes the F in this space of modular forms here to this space. And the other is to take a G which is in, so F is in this space, and then move it to this space. So we have these two maps. The space of modular forms that are spanned by these two maps is called the space of old forms. The space of old forms, so Sk of gamma of n, old, is a space spanned by the images of these maps as we vary over all possible factorizations. So you take your capital N, you go over all factorizations d1, d2 of n. For each d1 and d2, you have all these bunches of maps, and you have this mapping of the space of mk of gamma d1 for a subspace to this. And so these are all the forms that are coming from lower levels, and you take the linear span of that, and you call that sk gamma of n old, and these are called old forms. And the new forms are the orthogonal complement with respect to the Peterson inner product. So we can then write, we can decompose sk of gamma of n as sk old gamma of n direct sum sk new of gamma of n. And this is the orthogonal complement with respect to the Peterson inner product. Or firstly, as an orthogonal complement of as a vector space, or there's no orthogonality, just as a complement of the vector space. And then the orthogonality, it actually is the case that it's the orthogonal complement with respect to the Peterson inner product. So these are what are called new forms. And the problems that we were facing with respect to eigenfunctions of all the Hecke operators disappear if you confine your attention to what's called the space of new forms. And this is what Atkin and Lehner do in a very famous monumental paper written in the 1970s, which of course we'll not go into detail, but that's the basic theory with respect to the space of new forms. But these guys, these forms have the level, genuine level n, and therefore one can also talk about Dursley series attached to these things, get analytic continuation and functional equation. And if you remember your functional equations, they'll all have gamma of s's and n to the s's and so on and so forth. Where are the n to the s's coming from? They're coming from the level in which the thing lives. So it was very important to identify the level in which it's living, and so it's important to focus one's attention on the space of new forms. So that's more or less summarizes this particular little louder, what?
In the Deline's result.
In the Deline's result, yeah.
Is it necessary that P does not divide n, or in general?
I think P does not divide n in Deline's result, but I think in general it's actually still bounded by, yeah, I think the estimate is still valid, even in the other cases. One more point I should mention is maybe you can talk a little bit about the Atkin-Lehner involution, perhaps, yeah? So that Atkin-Lehner involution is a special matrix which is essentially 0 minus 1 n 0. This matrix is not an element of SL2Z because it has determinant minus n or determinant n, and but it is a transformation which acts on the space of modular forms of weight k on gamma naught of n, taking modular forms to other modular forms. And this particular involution is important when we study functional equations.